Hey everyone, welcome to this explainer. I'm absolutely thrilled to be bringing this to you on behalf of Forge College. Now, if you were with us for our previous lesson, the overview of Solana-program templates, you know we took a high-level tour of the static file layout in a typical project. But today we're actually bringing those static files to life. We're zooming right in on that exact split-second moment where the blockchain hands off a transaction to your code. This is literally where the magic happens, where raw bytes turn into real impactful actions. So, grab your developer hard hats because we are getting into the nuts and bolts of program entry points in practice. Here is a quick look at our roadmap for today. We're going to start at the execution starting line, outline the processor's strict job description, check out the template wiring, explore this awesome concept called the secure railway dispatcher, and then finally we'll build a minimal dispatcher in Rust. All right, let's jump right in. Okay, section 1, the execution starting line. Let's dive into this and see where things really kick off. So if you've ever wondered exactly where a Solana smart contract wakes up and starts doing its job, this is it. To really understand execution, we've got to talk about the absolute star of the show, the processor. Basically, the processor is your deterministic gateway function. Think of it as the crucial bridge between those static template files we looked at last time and your active executing program logic. When a user clicks a button in a dApp, the runtime fires raw instruction bytes right at your program. The processor is the very first piece of your custom code to step up and say, okay, I've got this, I'll take it from here, transforming those chaotic raw bytes into safe, predictable behavior. Right, moving on to section 2, the processor job description. So what exactly does this processor do once it wakes up? Well, let me tell you, it's incredibly particular. It has a very narrow, incredibly strict, and honestly, highly paranoid job. It trusts absolutely no one. It follows a super strict sequence. First, it validates top-level invariants, like is this even the right program? Second, it parses the instruction bytes. Third, it dispatches the request to the correct handler. And fourth, it maps internal errors if anything goes wrong. The absolutely crucial point to take away here is that the processor does not do the heavy lifting of your business logic. It doesn't calculate your token balances or update massive data structures. No way. It's just the bouncer at the door, checking IDs and pointing people to the right room. To actually pull this off, the runtime hands the processor 3 specific clipboards of information. First, it gets the program ID, which is just the public key of the currently executing program. Second, it gets an array of accounts. These are the files it's actually allowed to read from or write to. And third, it gets the instruction data, which is literally just a raw array of bytes holding the user's specific request. Once it's done its job, the processor absolutely must return a standard program result. This basically shouts back to the Solana network either success or hey, something went horribly wrong. Okay, let's take a look at section 3, template wiring and files. We know what the processor does in theory, right? So let's see how these abstract responsibilities map out in a real Solana project directory. What's really interesting about this architecture is how beautifully clean the blueprint is. Everything is separated perfectly. Entrypoint.rs does nothing but expose the program to the runtime and call your processor. Processor.rs is where our bouncer lives, parsing and dispatching. Instruction.rs defines the different types of requests your program can even handle. And finally, the handlers folder? That's where the actual specialized work happens. So if you need to fix a bug in how a user updates their profile, you don't even touch the processor. You go straight to the specific handler file. It keeps your whole codebase incredibly organized. All right, on to section 4, the secure railway dispatcher. To make sure all this abstract code stuff really sticks, I want to share one of my absolute favorite mental models. Let's imagine our processor as a secure railway dispatcher. Picture an old-school, grumpy, clipboard-wielding, completely no-nonsense dispatcher standing at a super busy junction. This perfectly illustrates how the parts of a transaction interact. The trains arriving at the junction, those are our transactions. The manifest the conductor hands over is our instruction data. It tells the dispatcher what the train is actually supposed to do. The train cars hooked up to the back are our accounts, the cargo we're processing. And the specific rail yards way down the line, those are our handlers. If the manifest is unreadable, or if a train car is missing a wheel, our grumpy dispatcher blows the whistle and stops the train right there. It doesn't even get past the junction. When we compare the two side by side, the contrast is pretty stark. The dispatcher, our processor, performs shallow, super fast checks, it does strict routing, and aggressively refuses bad cargo. On the flip side, the handlers, those rail yards down the line, are where the actual specialized labor happens. That's where you find the deep business logic, the state mutations, the real unloading of the freight. Because the handlers trust that the dispatcher already double-checked the manifest, they can just get straight to work. Listen, if you take literally nothing else away from this explainer, remember this core architectural mantra. Fail fast and consistently at the processor boundary. What does that mean for us? It means if anything looks even slightly suspicious, we reject the train immediately with a program error. We absolutely do not let malformed data sneak into our complex business logic where it could cause some devastating exploit. We stop it right at the gate. Let's move on to Section 5, Building a Minimal Dispatcher. Now let's see how this actually builds out in practice. We're going to translate our railway analogy into a minimal Rust dispatch snippet. And hey, don't worry if you aren't a Rust expert just yet, the logic is actually really straightforward. Here are the 3 steps our minimal code takes. First, it grabs the very first byte of the instruction data array. Think of this single byte as the track switch. It's an opcode that tells us exactly where the train needs to go. Second, we use a match statement to look at that byte. If it's a 0, boom, we send the train to the process init handler. If it's a 1, we send it to process update. Third, and this is key, if it's a 2 or a 99 or literally any other number we don't explicitly recognize, we immediately throw an invalid instruction data error. We don't try to guess, we just reject it. Now, when the processor routes the train to the handler, it does something super clever. The handlers receive a trimmed slice of the data. Because the processor already read that first byte, the routing opcode, it literally chops that byte off before handing the rest of the data array over to the handler. It's like ripping off the routing label before handing over the package. This means the handlers only deal with the cargo meant for them. They don't have to worry about routing logic at all. Okay, bringing it all together in Section 6, Conclusion and Next Steps. And just like that, we've completely decoded the processor. Let's wrap up this explainer by summarizing how this powerful pattern keeps our entire codebase clean, scalable, and most importantly, bug-free. Here are your practical principles for building a secure entry point. 1. Fail fast on malformed instruction data. 2. Map structural failures to a standard program error so the client application knows exactly why their transaction failed. 3. Dispatch by discriminant, that first opcode byte, to small, highly focused handler functions. And 4. Keep your error boundaries crystal clear. The processor handles the structural routing errors. The handlers take care of the complex domain logic errors. Honestly, this separation is a total game changer. It makes your code vastly easier to test and audit. Now that you understand the theory and you've seen the minimal code pattern, you are totally ready for the practical application. Next up in our module on understanding Solana-program templates, which sits within our broader Programming with Solana track, we will be diving into initializing and setting up a Solana-program template. We're going to drop this exact dispatcher snippet into a real scaffold and compile it, so make sure your Rust toolchain is ready to go. Before we go, I want to leave you with this to ponder. If your processor is the only gatekeeper to your smart contract state, what actually happens if the dispatcher falls asleep at the switch and lets bad cargo through? Security and Web3 absolutely starts at the front door. To explore the answer to this and to dive way deeper into everything we've covered today, I highly encourage you to visit forge.college to learn more about this subject and a wealth of other fascinating Web3 topics. On behalf of Forge College, thank you so much for learning with me today. Keep building, stay curious, and I'll catch you in the next explainer.